All right, we should probably get started. We're a little bit early, but it's my pleasure to welcome everybody to the first of 3 public lectures this fall. There's 2 more. Today, actually, the topic is very, very timely, and I'm not going to steal Professor Yelle's thunder on this, but we have two others, one on October 8th. I think it says the 8th. And this is by Professor Harris, who will be talking about, the big boundary, which is, well, again, I won't steal his thunder, but it has to do basically with the heliosphere. It's called the big bubble that was recently crossed by the Voyager spacecraft, so it's also very timely. And then in early November, on November 5th, if my eyes are correct on this, it's Professor Barman, who's an expert on extrasolar planets, also another booming area of research, and we'll highlight that research. The purpose of these public lectures is to highlight some research being done in the department. If you're not familiar with our department, let me just say that there's a long history here. The Lunar and Planetary Laboratory was established in around 1960 by Gerard Kuiper, the person for which this building is named, a famous planetary astronomer. We became a department in the early 1970s, a scholarly department alongside others in the College of Science like physics and chemistry and geology and so on. But you probably won't find a planetary sciences standalone department as broad as this one anywhere in the world, for that matter. It's one of the largest departments around, and we do research in a very broad array of planetary sciences, very broadly defined, from geology of planetary surfaces to the chemistry and physics of interiors and planetary atmospheres, the sun, plasma physics, asteroids, Kuiper belt objects, celestial mechanics and extrasolar planets and beyond. So there's a lot of research being done in the department. So the point of these public lectures is to sort of highlight some of that research. So this is a public lecture, but feel free to ask questions. In fact, that's the point. We want to have a lot of interchange, and today's talk is to be given by Professor Roger Yelle, who's a professor in this department whose specialty is the physics and chemistry of planetary atmospheres. He's interdisciplinary scientist for the Mars MAVEN mission, which is currently en route to Mars. It's due to arrive in about a week, and when it gets there, it will have quite a surprise waiting for it, and that's the point of today's talk. So it's my pleasure to introduce Roger Yelle.
Oh boy, this is different. You know, when I give lectures to the freshman classes, they don't clap. Thanks a lot, John. Thank you, everyone, for coming. I hope this is interesting for you. It's nice to see such a large and diverse audience. So this is just great. So I'm going to talk about this mission, which we call MAVEN, and MAVEN is an acronym. The M stands for Mars, the A stands for atmosphere, and I forget the rest. And it's a mission that's designed to study the atmosphere of Mars. In fact, a particular part of the atmosphere of Mars, the upper atmosphere. So I'll kind of describe that and describe what it's going to do and talk about this comet and things like that. But yeah, if you have questions, feel free to interrupt, and we'll have a question and answer period at the end too. I think it'll take about 45 minutes, but we'll see how it goes. Okay, so MAVEN is one part of kind of a NASA's Mars exploration program, and this view graph shows you some of the other missions in there. You probably heard about some of these. So there's like the Mars Science Lab, which landed on the surface of Mars a year ago last August, and is still roaming around collecting data. In fact, many of these missions are still operating. MRO stands for Mars Reconnaissance Orbiter, and if you walk through the hallways outside this building, you'll see these great pictures of the surface of Mars, and they were taken by an instrument built here at the Lunar and Planetary Lab that's carried on that orbiter. That's the HiRISE instrument. Mars Express is a European instrument. Odyssey you may have heard of too. MAVEN is right here, and these are missions that are kind of in the planning stages. So one thing this tells you is that MAVEN is not on the surface. It's an orbiter. It'll be in orbit around Mars, sampling the atmosphere as it orbits around. Okay. So
5,
I'm hoping the
3,
videos work.
2, 1.
This is
Main
launch.
engine start, ignition, and liftoff of the Atlas V with MAVEN. Looking for clues
About 9
about
months
the
ago.
evolution of Mars through its atmosphere.
So this is from the Cape, Florida, Cape Canaveral. It was a perfect launch. I was there. There was actually quite a good group from LPL there. A lot of the students came along, and if you've never been to a launch, I highly recommend it. It's really kind of an interesting thing to see. Okay, so it's on its way to Mars, and it'll get there. This is actually kind of an old view graph. Today is supposed to be September 5th, but today's actually September 10th, right? Yeah, so it's 11 days till arrival at Mars. It's going to get there at 6:50 Arizona time on the 21st, which of course is the equinox too. It's about a 10-month cruise, and let me see, these are details. TCM stands for Trajectory Correction Maneuver. All right, so you launch a spacecraft and you point it towards Mars on an orbit that goes towards Mars. But the orbit might not be perfect, and what you do is you take images of Mars. As you get there, you ascertain what the spacecraft position is, and you might have to correct the trajectory so that it actually reaches Mars. And maybe some of you are old enough to remember we've launched some spacecrafts that have missed Mars. So it's important to do this. And I'll talk maybe more about that a little bit later too. But this trajectory has been so precise that most of these correction maneuvers have been canceled. All right, so it's on track, and it'll be there shortly. This is a kind of a picture side by side of the Earth and Mars. This is where we live. That's where Mars is. They're very different. The Earth is much bigger. Mars is, kind of roughly half the diameter, much smaller in volume than Mars is, and the surface is also very different. The Earth is covered with water. The Mars is covered with rocks, and we're going to talk about that in particular because it bears on the kind of the motivation for the mission. One of the other motivation, now this is kind of overarching motivation for the entire NASA Mars program, is did Mars ever have life? This is kind of one of the main questions we'd like to answer. So Mars and Earth have some things in common, right? They're both these rocky planets that are kind of at an okay distance from the sun, not too close, not too far away. Mars is the fourth planet out from the sun. Earth is the third. It's got a rocky surface that you could walk on if you were there and you had some way to breathe. And it's got an atmosphere. It's got an atmosphere that's much, much less dense than the Earth does, but it does have an atmosphere. So in some sense, it's the planet in the solar system that's closest to the Earth, both because of its position from the sun, the fact that it's a rocky planet. We call them terrestrial planets, and that it's got an atmosphere. Venus has an atmosphere too, but it's got a horrendous atmosphere. It's much, much hotter and much, much larger than the atmosphere of the Earth, and it would melt cars and things like that. So if you had to pick sort of the nearest neighbor to the Earth, it would be Mars. So the question actually comes up, is there any life on Mars? So we've actually had missions, the Viking missions back in the 1970s, were sent to look for life on Mars, and they didn't find any. So we've adjusted our goals a little, and now we don't ask the question, is there life on Mars, but did Mars ever have life? And one of the reasons you might think about that has to do with the history of Mars. And I'll talk about this some more in the next hour, is that there's currently no liquid water on Mars. It's a very, very dry place. There is some water, but it's in the form of ice, because Mars is also a very cold place. Think like tundra, except a lot colder and a lot drier. But there's lots of evidence, I would say definitive evidence, that early in its history Mars had water, lots of water. And I'll show you some of that evidence. So then the question comes up, well, maybe there was once life on Mars when it had water. Or how far did progress towards establishing life on Mars go? We think life started because of natural chemical processes. How far did those chemical processes develop before Mars turned into this kind of barren wasteland that it is today? So we'd like to, kind of in even broader sense, we'd like to understand, why did these two planets diverge so drastically? Why did Earth go to this, the state it is in now, which at least current time is okay, right? It's kind of nice and it rains and there's water and stuff like that. It hasn't gotten too hot yet or anything. Maybe that's going to change. But, Mars went in a totally different direction and became kind of this frozen wasteland. So what's responsible for that? Why is the Earth like it is today and Mars so different? Okay, here's some of the evidence for water, and I'll show you some more later. I don't know, I hope you can see that okay. I think maybe this is the time when I dim the lights. When I do this with the freshmen, they fall asleep. So please don't. But all right. So, but I probably should have done it for that movie. But anyway, you can see here, and being from Tucson, you can recognize this as dry riverbeds on Mars. It's kind of unmistakable, right? And I'll show you some evidence later. There's carbonate deposits on Mars, and these are kind of minerals that are made in an aqueous environment like water. So this is some of the evidence that there was once water on Mars. In order to have liquid water, you need a much more substantial atmosphere. As I said, the atmosphere of Mars is very thin. The pressure is 6.6% that of the Earth. And it would have to be much greater, an atmosphere like the Earth in order to support liquid water. So what happened to the atmosphere? Okay, so we designed the MAVEN mission to investigate that. And I'll go into some more details about that in a minute. First, I thought I'd just like to tell you something about the spacecraft and the mission. So here's another picture of the spacecraft. It's a drawing. I'll show you some pictures too later. It's about the size of a school bus, at least if you count the solar arrays. What you're looking at here, these are the solar arrays. So it's solar electric power. That's what powers the electronics on the spacecraft, the sunlight. That's the radio antenna that transmits signals back to the Earth. Those are some of the scientific instruments and the antenna or other scientific instruments. So it's about as long as a school bus. It's about as heavy as an SUV. Here's the trajectory. So there's the sun in the middle. The Earth goes around the sun and something that's quite close to a circle. Mars goes around the sun in what we call an ellipse. It's kind of like a flattened circle. And I think you can see that if you look carefully at this. And so the job is to get from here to there. And in order to do that, you go on a trajectory that looks like that. And intercept Mars somewhere over here. And that takes about 11 months. All right, so launch was on 18 November. And what happens on the 21st is what we call orbit insertion. MOI, for Mars orbit insertion. So the spacecraft will fire its engines and it'll slow down and then it'll be captured by the gravitational field of Mars, and then it'll be orbiting around Mars. And right now it's orbiting around the sun. So we have to go from orbiting around the sun to orbiting around Mars. And that's in fact a multi-stage process. First you have this engine burn that happens on September 21st, but then there'll be a lot more sort of minor burns in order to get it into, make the orbit in the shape that we want it to be, which is shown over here. And we'll then be in an orbit that looks quite a lot like this with some slight changes for about 1 year. Science operations are scheduled to last 1 year. We're hoping it lasts longer. Once you get a spacecraft up there and it actually works, it's kind of hard to shut it off. So we don't do that very often. So if everything's working well, the hope is that it'll actually last longer than a year, but it should last at least for a year. Okay, where is it today? This is kind of impressive. Here's that same diagram before, and this was actually a few days ago. So there's the spacecraft, and there's Mars. So it's almost all the way there, and it's just clicking off the final kilometers right now. Okay, so here's a kind of a close-up of the spacecraft. There's scientific instruments sort of scattered around there. All right, some of the essential numbers up there again. Might want to notice the power. Well, two interesting things. There's the wet mass and a dry mass, and so a lot of the mass of the spacecraft is actually fuel. It's not so easy to get into orbit, and that's what that, say, more than or in 1,000 kilograms is to get into orbit and adjust the orbit once we're there. So the dry mass is the mass of the whole thing without fuel. And it needs about a kilowatt, about 1,000 watts, a little more than 1,000 watts of power to run all the equipment on there. The equipment includes the antenna and all the electronics that's required to drive it, and the scientific instruments. And that's all supplied by the solar arrays. And so in nominal configuration, or for much of its orbit, these solar arrays are facing the sun. And of course, the Earth, seen from Mars, the Earth is pretty close to the sun, and then the HGA stands for high gain antenna. It's like, I guess people don't have these anymore. Everybody used to have an antenna dish in their backyard. Basically, that's what it is. And it points towards the Earth. So a number of the instruments are on this articulated platform. So it's, for various reasons, it's useful to get the instruments away from the spacecraft because there can be electronic noise. And I find myself talking like an old person all the time now. When I was a kid, it used to be like your TV could get snow on it and make funny sounds and things like that. Like if you turned on the blender and the TV was on, you couldn't watch the television because you get all squiggles across the screen. I don't think that happens anymore, but some of you might remember those kind of things. It happens to scientific instruments too. And so you want to keep the instruments in what's an electrically quiet environment that's away from sources of noise. And so the spacecraft is a source of noise, and the instruments like it quiet. Also, this allows you to point, point places where it's articulated, so it moves, and in two axes. And so if these humongous solar panels, for example, are blocking Mars, you can still see around it because you're off on the end here. And during the course of the mission, this will move around and pointing into the proper configuration. There's some other kind of fixed instruments indicated around here, and I don't actually remember. Yeah, here it is. This kind of view graph shows you the instruments in more detail. So there's 9 essential instruments on the spacecraft, and these are things that are designed to study the atmosphere of Mars. I'll just tell you their names now, and as we go through this talk, I'll tell you a little more about what they do. There's a number of instruments that kind of measure the output of the sun, because the sun, exerts an enormous influence over the state of an atmosphere. It's true for the Earth too. But we need to understand what's going into an atmosphere, how the sun's shining on it, in order to understand how it behaves. So that's what these instruments are for. Some of them measure energetic particles from the sun. The sun not only emits light, but energetic charged particles, some electrons and some protons, and even some other stuff. And those will be incident upon Mars, ram into Mars, and affect the atmosphere. And these 3 instruments are designed to measure that. This one is designed to actually measure the ultraviolet light coming from the sun. Down here, this is another charged particle detector. It has slightly different properties than those. Let me see. On these, at the end of the solar array here, there are these little conical shapes, and those are magnetometers. So the Earth has a very strong magnetic field, right? Everybody's seen pictures of the Earth's field, which kind of, it's really important because it protects us from these charged particles that come from the sun. If the Earth didn't have a magnetic field, you wouldn't be here. If we sent an astronaut to Mars, he wouldn't make it. because he'd be outside the Earth's magnetic field and unprotected. So if you've signed up for this website where to be an astronaut to go to Mars, has anybody done that? Costs $10 or something, right? Maybe $30. Anyway, it's a one-way trip. Just be aware of that. And it's because of this magnetic field. Mars has a very strange magnetic field. It's rather than a big, strong magnetic field that protects the whole planet, it's got little localized magnetic fields on regions of the surface. And the idea is that those are remnants from what was once a much stronger magnetic field that disappeared over time early in the history of Mars. And this instrument here measures kind of the electrons in the atmosphere of Mars. And that instrument there, these are all acronyms. NASA loves acronyms. That measures the composition of the gas in the Mars atmosphere. So, the Earth's atmosphere is mostly nitrogen with, 20% oxygen and traces of water vapor and argon and lots of other things. The Martian atmosphere is mostly CO2 with some molecular oxygen and carbon monoxide and traces of water vapor and all kinds of other things. And that'll be measured by this instrument. This measures the various things about the composition of the atmosphere by looking at the UV light from the atmosphere. That's what the UV is for. And it can determine the temperature and also the composition of the atmosphere and things like that. So it's quite a sophisticated instrument suite. This is kind of the shape of the orbit and tells you the orbit's picked to be this shape for a particular reason. It's also elliptical, which means it's this squashed circle. And down here, it gets very close to Mars. It flies nominally about 150 kilometers above the surface of Mars, but on special occasions, it gets down to about 120 kilometers above the surface of Mars. That's quite deep, so it's actually skimming right through the atmosphere. And the reason for that is so that you can actually take samples of the atmosphere and measure it and see what's going on. But it also gets quite far from the atmosphere, up here about 400 kilometers away. And the reason for that is to get outside the atmosphere so you can measure these things that are coming into the atmosphere, primarily from the sun, but also from other places. And so you can measure the solar input and the solar wind, which is these charged particles coming from the sun directly when you're up in this region of the orbit. So that's why it's got that shape. Let me see. There's this thing called the solar cycle. The sun varies in this periodic fashion every 11 years. And you have solar storms at a time that's called solar max. And that's what this graph shows here. And you have a lot of sunspots. Sometimes you have a lot of sunspots at what we call a solar maximum and a solar minimum. There aren't many sunspots. So that's where the terms max and min come from. But the output of the sun also varies with this 11-year cycle. And it's kind of, I guess you have to say it's unfortunate that the sun's been really quiet lately. So back in 2000, kind of the solar output, and when I say output, I really mean the ultraviolet light from the sun was quite strong. There was lots of sunspots. It was kind of active. And this time around, 11 years later, it's maybe roughly half as active. And we were kind of hoping for a big strong solar maximum, but it looks like that's not going to happen. And this time here shows you when Maven's going to be at Mars. But there's some compensation, and I'll talk about that in a minute. Some more stuff about the spacecraft. Let me see. These are actual pictures now, not drawings. It was built in basically in Colorado, assembled at the Lockheed plant just outside of Denver. And here's some gnomes. Actually, working on the spacecraft in the High Bay area up at Lockheed, making sure the solar panels unfurl properly. And everybody's dressed up. You got to be very careful with dirt, make sure it stays clean, so it's a clean room. Okay, it's balanced, so it spins around nice and smoothly. It didn't fall over, didn't wobble. So that's images of the final spacecraft testing. and you put it on a very, very big plane and fly it down to Cape Canaveral, where some more gnomes dressed up in these white outfits. There's nice young men in their clean white suits. Anybody know what I'm talking about? Anyway, and gets put in. This is called a fairing that goes on top of the rocket. And it's getting lifted there, and this is kind of nerve-wracking. Okay, swung over and gets lowered down gently and then attached. Okay, and that's where the spacecraft is, sitting there on top of the rocket. I have to say that the thing about going to the Cape and watching this and this whole thing is it really impresses upon you what a tremendous collaboration is among thousands of people. I mean, tens of thousands of people had to do their job and do it correctly in order to send a sophisticated spacecraft to Mars. And it just impresses me that human beings can be that organized. Of course, we're not often that organized. I would say this is like the pinnacle of human organization and even goodwill. So it's really an impressive thing to see. And so everybody's very happy because it all worked out well. And somewhere in there is me. I'm not sure where. This is kind of, so pictures from various places. So that's the Cape. This is JPL, that's the Jet Propulsion Lab, which plays a large part in all these missions. That's Lockheed Martin, just outside of Denver. And that one I can't read from this angle. I think that's also JPL, NAV, JPL. These guys are legendary. They're the ones that steer the spacecraft to the proper location. Okay, and there's another launch picture. So everything's actually working quite well. We've actually seen Mars. This is our first look of Mars, and this is from the UV camera on board the spacecraft. This is a spectrum, which is the distribution of light from Mars as a function of the wavelength of the light. And it doesn't really mean much to anybody, but just the fact that it goes up here and comes back down again and kind of looks like that means that we've seen Mars. So it works. Mars is there. The instruments are working. The spacecraft's pointing properly, and everything seems okay. We've also been measuring, so the space between the Earth and Mars is not empty. It's full of these charged particles that come from the sun. And we can measure those, and we can measure them at Earth and at the location of Maven. And so here's the sun. It's sending out these charged particles, and they go on these kind of spiral trajectories. This is called a Parker spiral for the experts in the audience. And Maven can make measurements, and we can make measurements of the Earth, and you can see that if you connect it on the same spiral, you have very similar measurements. And so you can compare these things and understand what the sun is doing to the space in between the Earth and Mars, and then what's going to hit Mars when the charged particles along the spiral actually make it that far. And this shows a similar thing over here for some slightly different charged particles. Okay, so that tells us, these are, again, measurements made by the instruments on Maven, that large collection of charged particle instruments, and so they seem to be working fine too. So everything's good. So why are we doing this? And here's another picture of the Earth and Mars. And so if you look at it, I mean, I picked these out because it emphasizes the difference between the two planets. So here we live on this blue planet, right? It's blue because we have oceans. 3/4 of the Earth's surface is covered with oceans. So if you're an alien and you came from Mars around some other solar system, came to Earth, landed in some arbitrary place and took a picture, that's the most likely result you would get. All right? 3/4 of a chance you land in the ocean and you take a picture of the ocean. You do that on Mars, that's what you get. Okay, no oceans. It's just incredibly different. And why is that different? It's not the surface, really. There's places that look like this on the Earth, right? If you go to western Arizona, it looks a lot like that. And It's different because we have an atmosphere and we have water on the surface. And we think we have water on the surface because we have an atmosphere that allows that to happen. Mars does not. So what happened to the atmosphere on Mars and what happened to the water? That's the goal of the MAVEN mission. And let me see. It's kind of a theme of NASA. NASA likes catchy slogans. The slogan is "Follow the Water," and it's to understand, how these two, the evolutionary tracks of Mars and the Earth, could have diverged so drastically. But the other part of that is many people think that in order to have life on a planet, you need water, right? Because water, it serves as it enables a solution which large molecules can get together and grow into biological molecules. And so there's kind of a belief that you need water for life, and so that's the other reason we want to understand the history of water on Mars. So follow the water, and that's what we're doing. These are some more pictures of water. This is the dry riverbeds again. This is pictures of some kind of sedimentary deposits on Mars. This is probably the bottom of a riverbed long ago. And one of the things that's happened in my scientific career is we went from wondering was there really water on Mars? Because we had kind of weak evidence for it, say 20, 30 years ago, to today, I think there's no one that really doubts that anymore. It's really been determined. There's half a different lines of evidence. There are these images, which in themselves are fairly compelling. Over here I show a different kind of evidence. This is what we call spectral data. This is, you look at the reflection of a rock as a function of the wavelength of the light you're shining on it. And this is done with an instrument that's called CRISM, and that's on the Mars Surface Lander. And you can then identify the chemical composition of the rock. And I don't want you to worry about understanding this, but the point here is that we have these instruments that can measure the chemical compositions of minerals on the surface of the Mars, and that provides another line of evidence that there was water on Mars, because you see these minerals that are only made in the presence of liquid water. So I think it's definitive now. Once there was liquid water on Mars, it seems like that water was there a long time ago, early in the history of the solar system, but it's not there anymore. And so where did it go? Well, one possible explanation, or one thing we need to understand in order to understand the whole story, is how the atmosphere escapes. So Mars has this very tiny atmosphere now. The Earth has a big atmosphere. Maybe Mars once had a very big atmosphere, but it escaped. It escaped to space. And all atmospheres escape to space. The atmospheres are bound gravitationally, but there are various processes that can overcome the force of gravity and liberate gas in the atmosphere and make it go off into outer space. And the real heart of the MAVEN mission is understanding all of these, what we call escape processes. So one way to lose an atmosphere is if it gets too hot. If the atmosphere gets hot, then molecules are moving faster, and some molecules will be moving faster than the escape velocity. Okay, escape velocity is velocity that you have to have in order to escape the gravitational pull of a planet. So when we launched the MAVEN spacecraft, launched the rocket, we had to get the spacecraft moving faster than the escape velocity. On Earth, it's about 11 kilometers per second, and I should have converted that to miles per hour, but how many?
7.
You're right, it's 7. Is that right? No. No, it's 10. 10.76, I think. I'm sorry. All right, the number's not that important. All right, kilometers per second, and that's very fast. That's probably 20,000 miles per hour. I'm not sure I did that right. Okay, so it's got to go very fast. Spaceship has to go very fast to escape Mars. It's the same thing with molecules. And if some molecules are going very fast, because they're hot, they'll escape the atmosphere, and the atmosphere will go off into outer space. And after 1 billion years of that happening, you might not have much of an atmosphere left. There's other ways for the atmosphere to escape Mars. So if some of these energetic particles from the sun come into the atmosphere, hit the atmosphere, and these are going really fast. And they have lots of energy. They can make a big splash, just like dropping a rock into the water. And when it splashes, the gas that comes off can be going fast enough that it'll escape the atmosphere. We call that sputtering. And there are other processes too. You can have chemical processes that cause the atmosphere to escape, and various other things. And MAVEN's designed to study all of these things. It studies all this region of space around Mars, has that large suite of instruments to measure all this and really understand how the atmosphere is escaping. So that's the connection between this water planet that we live on, or the difference between our water planet and the freezing desert of Mars might be that lie in these what might seem like esoteric processes, which happen slowly but over billions of years, that could cause the atmosphere to escape. And Mars has no more atmosphere, nothing to keep it warm. You've probably all heard of the greenhouse effect, right? And now we're worried that the Earth has maybe got a little bit too much of a greenhouse effect. But the Earth always has some greenhouse effect. And if it didn't, it'd be a very cold place. The Earth wouldn't be very hospitable if there was no greenhouse effect. It's got kind of a greenhouse effect of just the right size. Mars has essentially no greenhouse effect because it has no atmosphere. And so if very early in its history it had a much stronger atmosphere, it would have a large greenhouse effect, it would be much warmer, and it could have had liquid water on the surface. So that's kind of the story. This is a movie of one of these escape processes, and so this wind from the sun, the solar wind, is coming in this direction. These little arrows show you the direction of the magnetic field associated with that, and this colored stuff flowing off Mars is the atmosphere that's being stripped off Mars because it's being bombarded by the solar wind, because it doesn't have a big, strong magnetic field the way the Earth does. So that's just, a scientist's calculation of one aspect of this atmospheric escape question. Now, I mentioned earlier that we wanted the mission to be there at solar maximum because we're thinking all of these things would be more interesting or more vigorous at solar maximum. Well, if we're at a half a solar maximum, they're still pretty interesting and pretty vigorous, and we can still measure them, but it's slightly disappointing. However, the universe gives and the universe takes away. Instead of solar maximum, what we've got here is this comet. All right, so here's the sun sending all kinds of particles and energy into Mars. And there's a comet called Siding Springs, which is also heading towards Mars. This is what Joe alluded to early in the introduction. And Siding Spring is named after an observatory in Australia, which discovered the comet. And I actually just learned today that this was part of the Catalina Sky Survey. And they organize observations not just in Tucson and on Mount Lemmon. Catalina Sky Survey is a program in this department which kind of studies asteroids and comets, especially near-Earth asteroids in the sky. And it's the largest such project in the world, and it's international, and this was discovered as part of that program. And there's an image of the comet, Siding Springs, on the sky. It's got this long tail. So it was discovered in January 2013, and for a few weeks after that, we were wondering maybe it'll actually hit Mars. It's not going to hit Mars, but it's going to come very close to Mars. It's going to pass within 130,000 kilometers. Now that may seem pretty far, but it's actually extremely close. So let me kind of explain that and tell you about comets. It's really four parts to a comet. What you see when you look in the sky are tails, and there's two tails, an ion tail and a dust tail, and they go in different directions, and if you have a really good comet, you can see them separately. The ion tail is made up of ionized gas particles, and that shine when illuminated with sunlight, and the dust tail is just what it is, small dust particles emanating from a region here where there's something we call a nucleus. And so that's actually a solid object, and we've seen a few of these now. There's a European spacecraft, Rosetta, that's now very close to a nucleus of a comet. Maybe you've seen some pictures of that. They're really bizarre looking things. It's basically a ball of dirty ice So mostly water, mostly frozen water, but with other things mixed in there like carbon compounds and stuff like that. It might be 10 kilometers, maybe 5 kilometers. In size, it's usually not a sphere, it looks like a rock. And because it's made of water, as it gets close to the sun, it starts evaporating. It warms up and it evaporates. And when it evaporates, then you start seeing these tails. So as it gets closer to the sun, you see the tails and you can recognize the comet. So the fourth part, that's 3, the fourth part is what we call the coma. And there's the coma is it's an atmosphere. It's a spherical, roughly spherical region of gas surrounding the nucleus. And so when the water evaporates, it goes into this coma. Some of the water gets ionized and goes off into the ion tail. When the water evaporates, it drags off some dust, and the dust goes into the dust tail. But there's this kind of quasi-spherical coma around the nucleus of the comet, which may be 100 or 200,000 kilometers in extent. So it's bigger than the distance between the nucleus of the comet and Mars. So this coma will actually impact the nucleus itself. Won't hit Mars, but Mars will go through the coma of the comet, and I'll show you some more about that in a minute. Let me see. All right, this is kind of a diagram. This is a diagram of the solar system. The sun's in the middle. Earth's out here, planet number 3. Mars is planet number 4, and this is the trajectory of the comet. And I've actually got a movie of this that'll be more fun to look at. So let me see if I can show you that. And this is the trajectory, Siding Springs, and on October 19th, it comes very close to Mars. That's basically as close to the sun as it gets, then turns around and goes back out again. It's also going sort of not in the plane of the solar system. All the planets orbit about in the same plane, but the comets don't. It's going in quite a different kind of orbit. So let me play that again. And the thing I really want to emphasize is how remarkable this is. Okay, so how many people have seen the movie Gravity? Okay, so in the movie Gravity, all these things in space are always bumping into each other, right? Okay, that never happens. Space is a very empty place, and it's a very long distance between any one object and any other object. These are very tiny things in this immense space. So what's really remarkable about this is these two very tiny things, this comet and Mars, actually come very close to colliding with each other. Okay, I estimated the chance of this happening in a year. The lifetime of the Maven mission is about 1 in a million. Okay, but it's happening, and that's just because space is so vast, and these things are all relatively small. Even a comet with a big coma is very small compared to, say, the distance between planets or the distance, the size of the solar system. It's very tiny. So this is an incredibly rare event. So we're really lucky, in a sense, that this happens. Even more lucky. So I told you the 4 parts of comets, but there's 2 categories of comets, what we call short period comets and long period comets. And these 2 comets categories or populations of comet come from different places. There's a picture of the solar system, and the short period comets, they sort of reside somewhere out here in the outer solar system, and then they periodically come in close to the sun where we can see them, or maybe closer to the Earth where we can see them. And the best known example of a short period comet is Halley's Comet, right? It's got a period of 76 years. So that's short, all right? And there's other comets with, periods that are somewhat shorter or longer than that. So, we know about a lot of them. There's a completely different population of comets, and these have orbital periods that are so long we can't measure them, all right? And what that means is that they come from very far away, all right? And they come from this region we call the Oort cloud, named after Jan Oort, a Dutch astronomer who first figured this out. So this is kind of an artist's drawing of the Oort cloud. The solar system is this little dot in here, so it's just immense. And it's populated by lots of comets that are out there in kind of a deep freeze. So the idea is that comets were kind of made along with the solar system 4.5 billion years ago. And as the solar system formed and we started forming planets and stuff, some of them got knocked out to great distances, but not so far. They didn't have enough energy to actually escape from the sun. They were just put far away from the sun on these very long orbits, kind of in deep freeze. So they've been sort of stuck out there in the freezer for 4.5 billion years. And for some reason, either the two of them bump each other, or a star goes by and perturbs them, or something like that. One of these things will get knocked in and will come into the solar system. We see that as the long period comet. Okay, so the point I want to make is, we love studying comets. There's lots of missions to comets and lots of people that study comets when they come by, but you can't actually have a spacecraft mission to a long period comet. And the reason for that is it takes about a year from the time it's discovered to the time it gets into the inner solar system, where we could send a spacecraft to greet it. But it takes a decade to make a spacecraft that can do that. All right. So by the time you don't have enough time. All right. Once you know about a long period comet, it's going to come and go before you can get ready to actually go investigate it. So the thing about Siding Springs and Maven is the comet's coming to us. We don't have to go to the comet. We actually, just because of this 1 in a million chance, we have this spacecraft up there, highly outfitted, in fact, very well outfitted for studying comets. And there's a Oort cloud comet that's solved the problem for us. It's going to come and visit Maven so that we can study it in detail. Okay, so that makes up for solar max not being so great. It's not only an opportunity, but it's kind of a danger, and we were quite worried about this in sort of the early days because of this dust tail, one of the 4 parts of a comet. Actually, let me go out of order here a little bit. The other thing I should tell you about, I'll come back to this, but just let me emphasize now. Comets move fast, right? It's kind of what the name has come to imply. And this comet is going to come, basically roughly 100,000 kilometers from Mars, but it's moving at 56 kilometers a second. Those are the measure, it's the way scientists measure speed. I converted this one. That's 126,000 miles per hour. All right, so it's going really, really fast. It'll go across the sky. If you were sitting on Mars looking up, it will go across the sky in about an hour. And it's just zooming by. And because of that, it's the gas particles from the coma that are incident on Mars. All right, so this is the actual image of a comet in UV light, where you can see the gas in the coma. And I forget which comet this is. It's not Siding Springs, because we don't have those images yet. But another comet. So these colors here represent kind of the gas in the coma of the comet. That's going to hit Mars. Let's see, there's Mars, and Mars is inside the coma. It's going to hit Mars at a speed of 126,000 miles per hour. And so that's a pretty strong wind, and that's going to strongly perturb the atmosphere of Mars. Okay, but there's also dust. And the dust is more of a worry because dust has more mass than gas does. All right? And so if you were, for example, to take a millimeter-sized snowflake, this piece of ice, and hit a spacecraft with it at 56 kilometers a second, chances are you would destroy the spacecraft. And so we were quite worried about that at the beginning. But there's a very large group of people did some very careful studies, and the results are sort of illustrated here. This is the dust tail that by looking with Hubble Space Telescope and other telescopes and looking at the dust tail of the comet, we're able to map the actual trajectories, all these individual dust particles. These dots are supposed to be dust particles coming off the comet, and get a fairly precise view of the dust tail. And here's Mars, and these are the orbits of various things. That orbit right there is Maven, and so Mars is just outside the dust tail. So it's not, we're not as worried as we once were, say 6 months ago. Yeah? Listen, but we're still a little worried because this is only a calculation, and what if there's something we don't understand? Or what if the comet does something weird? And sometimes comets do weird things, like they break up for no reason, or not no reason, but unexpectedly, and things like that. So there's still cause for concern, but basically we think we'll be okay. And again, that's pretty lucky. But nevertheless, we're taking some mitigation steps. So the other thing I want to emphasize is this comet gets to Mars on October 19th, which is less than a month after MAVEN gets to Mars. All right? So in fact, when a spacecraft gets to a planet, it's not supposed to start making measurements right away. The first thing you do is go through this checkout phase, where you make sure the spacecraft is operating properly, you make sure the instruments are operating properly, you kind of practice using the spacecraft, and that generally lasts a month or so. So this comet is showing up in the middle of this checkout phase. So we actually had to interrupt the checkout phase, redesign the entire kind of procedures for what the spacecraft is going to do. Another misconception is you shouldn't think that there's somebody like at Lockheed Martin or JPL or anywhere that's actually like sitting in front of a terminal or has got a dipstick or I don't know, a steering wheel telling the spacecraft what to do. It's all programmed in advance. It's programmed very precisely. Weeks or months in advance, you send up like computer code to tell the spacecraft exactly what to do, every millisecond. And so that was all done, and we had to throw it all out and do it all over again. So it's been a very busy 6 months, but we think we're ready. We are taking some mitigation strategies in case this comet doesn't behave quite the way we expect it to, and this dust is more of a problem than we think. One of them is kind of interesting, is we phase the orbit so that, as seen from the dust stream, Mars is kind of in the shadow of Mars when the dust stream comes by. So that, in that plot when I show you when it's closest to the edge of the dust, Mars, the spacecraft MAVEN will actually be behind Mars relative to the direction of the dust, so it'll have protection that way. We'll also turn the spacecraft so that the least sensitive surfaces are facing into the flow of the dust. And the third thing we're going to do is shut off a lot of the electronics because some of that could be damaged if the spacecraft was hit by dust and it happened to be on. So we're going to go into this hibernation kind of phase that lasts for a few hours when the dust might be at its peak, and then come out of it. We'll make measurements sort of before and after that. The reason to turn off the electronics is so we don't have any sparks. Okay, I talked about this a little bit. But the other thing I didn't emphasize was that this flow of gas from the comet onto Mars actually deposits significant amounts of energy. So it's going to really perturb the atmosphere of the comet. And that's the last thing I wanted to tell you about. And this is kind of getting into heavy-duty science stuff, but I just wanted to show you some pictures. Maybe look at this one down here. What this is the temperature of the atmosphere of Mars as a function of time. And the comet is closest to Mars at like time 10 hours here. And the temperature is going to rise, and it rises about 30 degrees. That's 30 degrees centigrade, which is a lot because the atmosphere of Mars is about 150 degrees centigrade. So the temperature is going to go up, what's that, 20%. And then it'll fall off with like a period of an hour. So it's those kinds of effects. We'll see heating in the atmosphere. It's going to be somewhat like what happens when a large solar storm hits the Earth, which you probably read about in the newspapers, might disrupt communications and things like that. Actually changes around the region of the Earth's atmosphere called the ionosphere, and that same region of the Mars atmosphere will be significantly perturbed by this comet. And this is really a sort of a nerdy view graph, but I just wanted to show you to make connection back to the basic motivation. This event, it will actually change the escape rate of the Mars atmosphere, the thing that MAVEN is there to measure. And that's what that view graph shows. This is kind of a measure of the escape of hydrogen from the atmosphere of Mars. And it should vary as a result of the comet input. And so we can study that, and that'll actually gives us another way to understand the escape of the atmosphere. Because we have this complicated system here, and we're perturbing it in various ways, or the universe is perturbing it, and we can see how it responds, and that'll help us understand better how it operates, which is kind of the goal of our mission. So I went way over time, so I apologize, but I'm done now, and I'll thank you for being here, and I'll take any questions you might have.
Are the solar arrays already fully deployed, or are they waiting to get into orbit before they completely open up?
No, they've been deployed for quite a long while now. I mean, essentially when we left the Earth's atmosphere, because we needed the power during what we call that period in between leaving Earth and getting to Mars, cruise phase. And so spacecraft's not doing a whole lot in cruise, but it is operating. So we needed the power in that phase, so they opened quite early. Yes?
Is Silent Spring going to be visible from Earth at any point?
I think with the telescope. The thing is, it gets to Mars at basically midday on in Tucson on the 19th. So you won't be able to see it from Tucson, but if you're on the other side of the Earth and you had a telescope, you could see it. Yes.
What other of the instruments we've already got up there?
All of them. Basically, everybody's trying to do something. Even the I understand that even the cameras on the rovers on the surface are going to look up and try to see it. Now, in fact, some very interesting data will be taken by this HiRISE instrument that's on the Mars Reconnaissance Orbiter, which is a highly capable camera, and that'll be able to see the nucleus of the comet, which is we haven't been able to see many cometary nuclei, and so that'll be really interesting, and that's one I'm looking forward to. Yeah?
How's it going to mitigate the HiRISE?
I'm not sure what their plans are, to be honest. I've been so tied up with MAVEN that I haven't been able to follow the other spacecraft. Does anybody here know any HiRISE people in the audience? And the thing was, we already had enough to do in order to get MAVEN operating at Mars, and then this comet shows up, and it's like, so a lot of things fell by the wayside, and anything basically not to do with this event. Yes?
Oh, sure.
There isn't any surface water on Mars, but is it possible that there's an aquifer below it, kind of like we have aquifers here on Earth? And would this spacecraft find that at all, or?
So there's no, we're not studying the surface. We're just studying the escape processes. And there's it's more like a tundra. There's frozen water in the what we call the regolith of Mars, the regions of the surface, just below the actual surface, regions of Mars just below the actual surface. If you go deep enough, there's always been speculation about some liquid water at depth. I don't really know where that is right now, but certainly nothing like oceans or not a large event, large inventory. Yes?
Do you expect the material that the comet will obviously deposit in the Mars atmosphere to significantly affect the composition of the atmosphere, or would that be a very temporary episode?
Well, maybe is the right answer. So certainly, for some elements, that'll be the case. I've looked at hydrogen, for example. So the Mars has a lot of oxygen because it's got CO2, and the basic thing coming off the comet is H2O. So if you add oxygen to Mars, you don't change it all that much because there's already a lot of oxygen, but the hydrogen will be a more significant perturbation to the atmosphere. So that's quite substantial. Even more interesting would be other elements like sulfur is an interesting one, for example. Mars doesn't really have any sulfur in its atmosphere, but comets sometimes do. We don't know about this one yet. If it has a significant amount of sulfur, you may end up with sulfur compounds in the atmosphere that were never there before. They could be there for a while. It kind of depends on what part of the atmosphere you're talking about. What will happen is they'll be deposited in the upper atmosphere, and then they'll slowly diffuse down to the lower atmosphere. And it may take weeks or months for that to happen. So you could perturb the atmosphere for kind of that length of time. But that's one of the things I'm really looking forward to, and I I hope we get some good information on it.
So Roger, I have a question.
Yep.
So with the deposit of this energy, the atmosphere will presumably expand a little bit, and that may lead to degradation of the orbit. Is that not an effect at all on Mars?
It's not. It's pretty small. I mean, I calculated that right away. I was kind of worried.
Because that's a big
But,
effect on Earth when
yeah,
you
yeah.
have big solar storms and things like that.
I mean, it's safe. It's the thing about the Mars atmosphere is highly variable, and the densities at the levels that the spacecraft fly through, they vary by a factor of 10. So you already have to have that margin built in. So we're small compared to that variability, I think. And so it shouldn't be an issue. Another one down here in front. Yes.
Is the energy, you talked about the rise in temperature of the various layers, upper
Yeah.
layers of the atmosphere. Is that enough to impact dynamics of the atmosphere on some measurable scale that the surface, Mars Science Lab or other things will be able to measure change in wind, in dust, in clarity, I don't know, other physical parameters?
I don't think so. I think it'll certainly change the dynamics of the upper atmosphere, kind of the ionosphere region and around there. I have some colleagues that are kind of looking at that. But I don't think there's enough energy to actually, it takes a lot more energy to change the winds at the surface, and I don't think there's enough energy for that.
Yeah, what would you say with the slide that you had of the various schemes of the atmosphere escaping, which way do we think is the predominant theory, at least right now until MAVEN does its thing?
So it depends on what part of the atmosphere, which molecules you're talking about. So for hydrogen, for example, or molecular hydrogen or atomic hydrogen, it's probably this thermal escape that the molecules are just moving fast enough to be going greater than the escape velocity and leave the planet. We call that Jeans escape. For oxygen, it's probably different. It's probably a chemical process, and there are chemical processes which break apart oxygen molecule into two oxygen atoms, and when that happens, they're going at high velocity, and some of them are going greater than the escape velocity again. We call that photochemical escape, and so right now that's thought to dominate for oxygen, and the thermal escape's thought to dominate for hydrogen, but that's in fact what we're going to test when we get there. Yes?
Is there enough known about the comet yet to estimate the temperature?
No, I don't, maybe somebody in the audience knows more than me. I think it's so long that, it's longer than the lifetime of human civilization. It might be longer than the lifetime of the sun. I mean, it's very, very long. And I mean, it comes from so far away that as far as you can tell, it came from infinitely far away. There's really no measurable difference between the two. Now, we think it comes from this Oort cloud, but it's just a very, very big orbit, and it's so big, it's hard to tell exactly how big it is. So don't wait, it's not coming back. Now, the short period comets are, one way to make a short period comet is a long period comet, comes around Jupiter, gets perturbed by Jupiter's gravity, and then gets captured into a shorter orbit. But Mars is so small, it can't do that to a comet. So Mars actually has very little effect on the orbit of this comet. It's really just determined by the sun. So that won't happen with this one. Okay, I think it's time for dinner.
Okay.
Thank you.